Welcome to the RSE. My name is Paul Bishop. I'll be chairing this meeting tonight, and it's my great pleasure, as I say, to welcome you to the RSE. The RSE is Scotland's academy, consists of peer-elected fellows, and covers a range of activities, and one of which, of course, is bringing the best of research, both in the sciences and the social sciences and the arts and humanities across the whole spread, the whole range of research and the disciplines of intellectual pursuit, bringing those to the public, as well as pursuing those in the context of the highest quality research within our various disciplines. So the topic is clearly of great interest, and in many ways the interest has been stimulated by the recent Typhoon Haiyan, which has many impacts on the coast which are in some ways similar to those of tsunami. And so it's great pleasure to be able to have David Tappin here tonight to speak to us. David is visiting professor at University College London and works for the British Geological Survey. David is a marine geologist. He's had more than 4 decades of experience of mapping the seabed, and mapping the seabed is one of the key issues in generating tsunamis, in generating the wave that then inundates the surrounding land that the wave hits. David's worked on tsunami for almost 15 years now, starting in 1998 with the tsunami in Papua New Guinea, which killed over 2,000 people. And he's worked on several events since then, and in particular the 2004 tsunami that we all, I'm sure, are very conscious of, which killed more than 200,000 people. So we're upwards of 250,000 people in recent years that have been victims of tsunami. So it is a major issue associated in particular with increasing populations along coastal areas, and particularly those in low-lying coastal areas. So it's great, with great pleasure, that I welcome David to Edinburgh this evening and invite him to speak to us now. Thank you, David.
Thank you, Paul, and thank you all for coming this evening and showing your interest, obviously, in tsunamis, but particularly with natural hazards. And actually, my first slide actually refers to the cyclone from the Philippines, which I'm sure we've all been following. And again, to me, who studies the hazard from tsunami, it brings many of the problems that we face in identifying and mitigating against these events, and in this context certainly saving people's lives. And you've probably been reading there are at least 2,500 people have been killed so far, but because of the isolation of many of the areas which have been hit, it's expected that certainly there will be a lot more casualties reported over the coming weeks and months. Again, we have major devastation. On the bottom right here you can see an image which to me is very similar images from Japan, where you have major objects picked up, in this instance a very large ship. And again, the magnitude of the cyclone was underestimated. They reckon there's going to be maybe 700,000 people who are going to be displaced. And again, there's a financial cost, but also the human cost. And again, we have what seems to be quite a slow aid response, and we've certainly seen that, and as far as the Indian Ocean is concerned. But returning to my theme of tsunamis, as Paul said, I've been researching these for at least 15 years, and 20 years ago few people knew about them, and I used to, and I still do, use this cartoon, which comes from 1985, which the woman is sitting on a beach, maybe somewhere in Indonesia, on Bali, and she's looking at her husband, and he looks exactly like one of our older directors, and she's saying, it sounds like they're saying tsunami, whatever that means. But of course, these days, most people are very much familiar with what tsunamis are. And although I'm talking about recent events and how we've learned, tsunamis have been known from historic times. And certainly the Greek historian Thucydides, I'm not sure if I pronounced that correctly for the classical scholars amongst you, and in the 5th century BC. And again, the Roman historian Marcellinus reported on a major event in the Mediterranean, the 365 tsunami, which has been very well researched and which actually we still don't quite understand. And again, coming from the to another aspect, Atlantis and the stuff of legend, the eruption of Santorini in the Aegean Sea in the eastern Mediterranean 3,500 years ago, and was there a tsunami, and did it lead to the collapse of the Minoan civilization? And there are indications, suggestions that perhaps this was not just a major eruption, but the associated tsunami, which could have had this major societal impact. And in fact, I'm leading a major project now which is trying to actually identify whether there was a serious tsunami. And coming closer to the recent event of 2011 in Japan, the tsunami in 1792 from Mount Unsen left 15,000 people dead, and this wasn't from an earthquake, but this was from a major volcanic collapse. And it's one of the first artist renditions that we have from one of these events. On the left-hand side, you can see the before, and subsequently on the right, you can see the after situation. And again, coming back to Japan, what we have seen there is amazing video images of the actual tsunami itself. And this is from a helicopter watching the tsunami waves come barreling in from the ocean and coming in at quite amazing speed. And as we come towards the right, you can see that the inundation of the Japanese coastline. And I will, and many of you will have seen this on the TV, and I'll be returning to this later in my talk. And again, with Japan, there was massive destruction, over 20,000 people died. And the images, which are similar to those that we're seeing of Cyclone Haiyan. Well, I'm not going to, I'm going to give you a very quick run-through of tsunamis, but I don't expect any prior knowledge. So for some of you, it would be a primer, for some it would be a refresher. And so part of my talk will be providing a background on tsunami mechanisms, and I'll be touching not just on earthquakes, but certainly on submarine landslides, and again focusing on the recent events which has led us to better understand these major natural hazards, the Indian Ocean 2004, again Japan, and other lesser known. And Paul has always mentioned that I carried out research on the Papua New Guinea event in 1998. And at the end of this talk, hopefully you will know as much as I, and you will go away perhaps better educated. And of course, the Indian Ocean event, as Paul has mentioned, 220,000 people died, and out of 300,000 since 1900. And these are images which, again, I'm sure many of you will recollect. On the bottom left there, you have Banda Aceh, about 120 in northern Sumatra, about 120,000 people died there, and again, an image of a ship which has been carried inland on Thailand. And one of the major importances of these events is that we actually learn from them. And certainly in 2004, it led to a major review of our understanding of earthquakes, and I'll be going into some detail in that later. But not only that, many natural hazards, such as volcanoes and earthquakes, happen to somebody else. And in this instance, in the Indian Ocean, because it was such a popular tourist attraction for Europeans, there were many, many tourists involved, and there were lots of videos, which again were broadcast and again brought us home. It was a major European disaster, and the worst natural disaster that Sweden has ever experienced, with 550 Swedish people killed. And I think about 150 British people that died. Here we go, about 150. And it was massive press coverage. I can't remember any other event which has been on the front page news for 6 weeks. And here you can see there's a bit of a cartoon on the top left, the wave of death. The horror emerges, and there you can see the Swedish lady, which I showed you in the previous slide. And then as we go from left to right and then down, you can see as we get to the bottom right, we get back to the important things in life about what our favourite soap stars are doing. And actually the Corrie, the Corrie headline there actually is, it's art mirroring life, if some of you recall what's happened recently. And again, recently this year there was a film called The Impossible, which dealt with the Indian Ocean. And it was based on a real-life experience of a Spanish family, and I went to see this film with not very high expectations, but it's certainly a very realistic and dramatic reconstruction of what happened on a beach in Thailand, and it's certainly one of the best visualizations, CGI, of a tsunami which I've ever seen. And it's a 10-minute sequence. The beach where it was the resort was in Thailand. 3,000 people died there in 2004. And the actual 10-minute sequence took over a year to film. And again, coming back to the Indian Ocean and the casualties there, and hopefully how we have improved, is that 220,000 people died. I've already mentioned locally 120,000 people died in Vanuatu, but 100,000 people died further afield in what we call the actual far field in India and in Sri Lanka and Thailand. But there was 2 hours warning for this event. There was 2 hours warning, and because there wasn't a warning system in the eastern Indian Ocean, those people died, and they died needlessly. Fortunately, things have changed. There was plenty of time for evacuation, no warning system, no evacuation, and they had very little chance because, again, a lot of people didn't understand what tsunamis were. There were odd occasions where there was a child on a beach who'd obviously received the best of British education who said, "It's a tsunami, let's get out of here." And so people were saved. And a few definitions about tsunami generation and propagation. Now I've given you some sort of background. Tsunami is obviously a Japanese word. It means Su and Nami and harbour wave. And that's because one of the first indications that people can have of a tsunami is when the actual initial wave enters a harbour. And I've shown you a little video there. And again, most tsunamis on Wikipedia, if you go on the web, are actually recorded from Japan, about 50% certainly over the past 100 years. And again, this is another image. This is from a location on the Sendai Plain on central Honshu Island. And you can see that the whirlpool effect, which gives the actual name to the terminology. In my opinion, tsunami is one of the most dangerous of geological hazards, and that compares with earthquakes and volcanoes, because it's of global extent. And what you can have is you can have a tsunami generated, for example, off the west coast of Chile, South America, which can travel all the way across the Pacific and strike Japan maybe 36 hours later and still be dangerous. So it's dangerous both close to the source, for example, an earthquake, but certainly far afield. And this actual time sequence is one of the most important aspects of our development of our tsunami warning systems. And again, coming back to the earthquake sources of tsunamis, the reason that we have them is that because of plate tectonics, and I think that many of you will be aware that the surface of the Earth is in constant motion. And along the red lines, and this is because there is crust generated along the red lines on this figure here, the so-called mid-ocean ridges, and the crust moves outwards. Something like 5 or 6 centimeters a year, about the speed that your fingernails grow, if you want some sort of comparison. But if you're creating this crust at one location, because the surface area of the Earth is reasonably constant, then you have to destroy it somewhere else. And it's along these what I've marked here as the plate convergence, along these yellow lines, that the actual crust is thrust back into the center of the Earth. And of course, although the actual plate creation, the crust creation along the red line is fairly constant, when it's thrust down into the mantle, into the center of the Earth, it's not. And what you have is you have a locking, and you get pressure build up, and then at certain occasions, here's a little figure, on the left-hand side, you have the crust going down, under thrusting the land on the right-hand side, and it pulls it down. And then you have an earthquake, there's a break, fracture, and the overlying crust jumps up. And that's what creates the tsunami. And along convergent margins, as I put here, they are quite dangerous places, and this is where you get most tsunamis generated. And again, another simple diagram. On the right-hand side, the overlying crust is pulled down, and it jumps up. And obviously, you can see from this figure, you have to have an earthquake under the sea to create the actual tsunami. And the comparison is, it's a ripple in a pond, throwing a stone in a pond, and you can see the ripple propagating outwards. This is a simulation. If you have an earthquake which is linear, obviously that wave will be a linear wave. And not all earthquakes cause tsunamis. This is a figure from the Indian Ocean event of 2004 when the earthquake was a magnitude 9. And you can see that it starts at the bottom and it propagates northwards. And on the right-hand side, what you have is the crust is uplifted. And on the left-hand side, the crust subsides. And that's one of the reasons why you get the negative wave, often on a coastline, which I'll mention. But we need an earthquake larger than magnitude 7. So really, tsunamis are created all the time because we have earthquakes underneath the sea, but they may be only a few centimetres high. A little while ago, a month ago, I was out in Crete. There was a 6.2 magnitude earthquake offshore, and there was a tsunami registered, but it was only a few centimetres high. But we need the big earthquakes to generate these very dangerous tsunamis which travel all the way across the ocean. And how the wave at the surface of the ocean is formed is if you have an uplift at the seabed, then the actual energy propagates through the water column. And it says here you pushes the water wave upwards, and the comparison, it creates like a step in the ocean. So you have a step, and once that step is created, it collapses under the force of gravity, and when it collapses, that's what creates a tsunami. And again, you have a positive wave where you have the uplift on one side and negative wave on the other side, and the wave propagates outwards. And at the ocean, it's fairly benign. It's mainly only a few, with earthquakes, it's mainly only 10, 20 centimetres high. And it propagates outwards, it says here, at very, very rapid speed, something like the speed of a jet airliner. And the wavelength is very, very long, hundreds of kilometres, but the height is very small, the elevation. And it's only when it gets to the actual coastline, when you get a shelving coastline, that you have bottom friction. And what happens as the energy interacts with the seabed, then the actual wave slows, and the wavelength, the distance between the wave decreases, and because of conservation of energy, that's when you have the amplitude increasing, and that's when it's obviously very, very dangerous. And when we look here at a tsunami caused by the Indian Ocean, you can see the wave propagating outwards, and you'll notice, although it's linear at the beginning, it bends and refracts, and that is because it's controlled by seabed morphology. And with these waves, tsunami waves that are created, we call them long waves, I won't go into too much detail, the frictional effect on the seabed can change the way that they propagate, and because we have a very good understanding of seabed morphology, the depth of the ocean, we can now model these events fairly well. In the Indian Ocean, the tsunami was for the first time measured by the Jason satellite, and you can see here the black line which runs down from the northeast to the southwest, and on the bottom you can see the wavelength that was actually measured. And one of the aspects of this is it's not just one wave. A tsunami wave is formed of a number of different waves, and that's, again, best to understood by the pebble in the pond. And you get oscillations of the water column. You get the initial wave, which is created, and it collapses, and then it oscillates. And again, if the earthquake is large enough and the wave that's created is big enough, then the wave can propagate around the ocean. If you look at the bottom right there, you can see, you can see the hours since the event, and you can see by the time it's about 15, 20 hours, it's going to strike South America. And although the wave is traveling these distances, fortunately, because there is some dissipation and reduction in energy, the actual wave height does decrease. And with the instance of the Indian Ocean wave, it traveled around the Earth about 3 times. And to give you a better understanding, this is a simulation from an eruption, and you can see the first wave, and it collapses, and then you can see the oscillation as it generates outwards. And it's normal that the first few waves are quite dangerous, but thereafter, obviously, they decrease, and therefore they are less of a hazard. And here again is another simple diagram which shows the wave generated across the ocean, and you can see the wavelengths here, about 200 kilometers. And then when you get the interaction of the energy with the seabed and the wave slows down, then the actual amplitude increases. And here you've got something like a wave of maybe about 10 meters when it strikes the land. And here's another little model here. The tsunami wave comes in, and as it approaches the shore, what you'll see is the actual wave, the actual seawater recedes, and that is because it's the negative wave which actually approaches the shoreline first. The sea recedes, and then what you have is the actual wave builds up. The different individual waves build up together, and then they obviously have this amazing effect on the coastline. And again, a bit of a comparison here: an 80-foot wave, something like about 30 meters. And for example, in Japan, some of the waves were something like about 15, 20 meters. You can see the scale with a human, and if you're obviously facing that, there's very little chance of survival. And this is a flow-through, a fly-through over Thailand after the Indian Ocean event. And it's Khao Lak Beach, where the film The Impossible was filmed, and you can see the brown areas of where the tsunami has inundated the land and created destruction, and the actual inundation limit there is something like about 1 kilometre, maybe 2 kilometres. And I want you to remember, this is north of Phuket Island. And as we come over this hill here, this is Khao Lak Beach. I'm going to show you a video from that location. And here you can see the devastation. There's a lot of major tourist resorts here. The inundation limit was 2 kilometres, and I've said about 3,000 people died here. And when we come to a video looking down on the beach, this is a tsunami flooding inland. And it looks quite benign. Apart from the fact it's a roiling torrent, you would think it was an ordinary wave. But then as we focus in, you can see the man. And as you can imagine, if you were faced with this, there would be very little chance of survival. And this is one of the aspects of a tsunami, because basically it's as if the whole of the water column is in motion, and it's just like a river in flood. It's a spate. And just a comparison, how the tsunamis compare to storm waves. They are unlike. This is the classic tsunami image, which is the icon of Tsunami Scientist. It was painted by a famous Japanese painter in the 19th century, Hokusai. And you can see Mount Fuji in the background, but we do know actually this is a storm wave rather than a tsunami wave. And when we look at a simple figure, tsunami versus wind waves come and go without flooding higher areas, unless you have a major storm, as we've seen with Haiyan, and then you can get major inundation. But the actual height of the waves is not great, and I think the Haiyan waves are something like about 5 meters, and that's with focusing. But the tsunamis come in, and they made a film in 2005 about one of my expeditions, and they called the film The Unstoppable Wave. And actually, that's what a tsunami wave is best compared to. And I give talks because there seem to have been so many tsunamis over the past 10 or 20 years, called the Age of Tsunamis. And do we live in this particular age, like the Renaissance or the Great Depression? And sometimes it seems to me that this is the case. And when we look, certainly over the past 50 years, large earthquakes up in the northeastern Pacific, the largest earthquake ever recorded in Chile in 1960, a magnitude 9.5, which again travelled across the Pacific and killed a number of people in Japan. The tsunami wave was something like about 3 or 4 meters high. 1964 in Alaska was very important, and it was the creation in the Pacific of the tsunami warning system, and that's one of the positive aspects of tsunami warning globally, is that there's been a system actually in the Pacific for over 50 years. And then, of course, Papua New Guinea, which I'll be talking about in a little while. Most recently, again, 2010, magnitude 8.8 in Chile. Sumatra, of course, the Indian Ocean event of December 2004. And most recently, yet again, Japan. So certainly over the past 10 years, you can see that there seem to be 20 years. We seem to have a number of very large events. Earthquakes are the major tsunami sources, but there are other ones. And a lot of our research on these other sources, tsunami generating mechanisms such as volcanoes, and submarine landslides have been carried out over the past 10 or 20 years. Up until certainly 1998, we didn't really believe that these other events, and this is an image from Papua New Guinea, they could create these very dangerous tsunamis. And as far as going back longer term, until the 1920s, we didn't really recognize that the ocean deeps were very active. I said there was a Grand Banks landslide in 1929. The reason that we understood it was there were these transatlantic cables which were broken. And people in America and England were talking to each other, and then they were broken off, and they phoned the GPO, of course, which is now privatized, so it's working much better. But they were told, oh, it was nothing to do with us, mate. And nobody really understood it until they went down, and you can see the top right there. There's a photograph of one of the broken cables. One of the major aspects of this event was we recognized that that there was something happening in the oceans that we didn't understand previously. But it created a tsunami, and 28 people died, and it was one of the seminal events. But it took us a long time, because of the technology that we have now, we didn't have then, to actually recognize this. And again, coming back closer to home, 1969, in the Gulf of Mexico, there was a major seabed failures, and this is caused by a cyclone, probably similar to Katrina, which happened about 5 years ago, and compares with the Deepwater Horizon event, although that was human failure rather than natural failures. But the important aspect of this is that the seabed can collapse, and not only can it create destabilization for engineering structures, but it can also create tsunamis. And now my first case history is Papua New Guinea in 1998. A tsunami wave 15 meters high came in along this very low-lying lagoonal area, the Sasana Lagoon, which you see on the top left, and over 2,000 people died, and you can see the images are very similar to Haiyan and also from the Indian Ocean and also Japan. And it was the first time really, although we were somewhat aware that maybe the movement of sediment on the seabed can be very, very dangerous indeed. And I put on the bottom right there a slump, which took place, or a subaerial landslide off the coast of Yorkshire about 10 years ago. And this is the sort of thing that could happen actually on the seabed. The Papua New Guinea event was important not only because of what we discovered, but how we did it. And today we can map the seabed with the same sort of accuracy that we can on land by using the propagation of sound in the water column. And what I put up here is what we call a multi-beam bathymetry map, which is basically a map of the seabed depths. And we can look at this, and for example, this is a convergent margin. Someone with experience in these areas can interpret a lot of the seabed features in terms of movement and tectonics, whether they're faulting, whether they're being uplifted, whether they're being eroded. And on the bottom there, you can see that went out there for 10 days, and we mapped 19,000 square kilometers of seabed, and I haven't got a good comparison about what that would be on shore. And just basically a couple of slides here. The technology is based on transmitting sound in water, and some of you might be sailors and you have an echo sounder on your boat, and you can send out a sound pulse which reflects from the seabed. It comes back, you can record that. If you can record the time, because we know the velocity of sound in seawater, then we can tell the actual water depth. And on the right there, you can see there's an image of the actual seabed. And here's a little video. And not only now can we just record the depth of sound beneath the ship, we can send out a wide, what we call a swath, like a cone of sound, and we can hoover up the seabed. It's a bit like mowing your lawn, and you can see on the right-hand side the little video, and the ship is moving along. I think it's going towards us, and behind it you can see it's recorded the seabed morphology, and this means that we can map the seabed with not only accuracy but very efficiently. And actually now we have pretty much mapped all of the oceans to some degree. And one of the important things of Papua New Guinea, it's the first time we actually mapped the seabed to find a tsunami source. There was a major tsunami, there was a very small earthquake, and 2,200 people died. And we carried out 4 or 5 marine surveys using high technology to try and find out what the actual source of this tsunami was, because the earthquake magnitude was very, very small. It's only about a magnitude 7. And the earthquake location we knew was here. And actually, by mapping the seabed, we found a sediment movement. We called it a slump. some of the observations are shown in this slide here. And one of the aspects of this was a 15-meter high tsunami for a magnitude 7 earthquake, which, as I've said, is pretty much impossible. And we have this particular peaked run-up, because that is, whereas an earthquake is linear, it's long, hundreds of kilometers, and you get a linear wave propagated outwards, traveling outwards. Submarine landslides are point source, and it's like the image I showed you of the pebble in the pond, where the actual tsunami wave was actually circular. And there are other aspects of it, that the earthquake epicenter, the source of the earthquake, was in the wrong spot. And there's also a 20-minute delay between the actual earthquake and the tsunami. So we went out and we carried out these sophisticated mapping. And you can see on the right-hand side there is a sort of failure, and it's very much like the image I showed you from off of Yorkshire. It was a slump. It was actually quite small, and we also sampled it. And down the bottom right, you can see there is a core of the sediments which failed, and they are clays. So the clays stick together, and when they fail, they don't travel very far. But if they travel fast enough, then they can generate the tsunami. Not only did we map the seabed, you can see the image in the middle, and the mound is where we think the actual slump was, but we went down with a remotely operated vehicle and also diving. And we actually had images of the seabed, and the importance of these images was that we could get some idea, one, that the seabed had moved, and you can notice on the yellow arrow there that there's like a fissure, and it looks quite degraded. And when we come to this fissure here, it looks very sharp. And our interpretation of that was that where we had the arrow I've just shown you, that probably moved more recently, and that was in the area where we thought that we'd found the slump. And we also found evidence of fluids which were coming out of the seabed. And we also found, you can see the mussels there, we're down at 1,500 meters, we're out of the photic zone. And these are these chemosynthetic organisms. Some of you will have heard about the hot smokers, which we find along mid-ocean ridges. But these are what we call chemosynthetic. They live off methane. And there was a huge proliferation in the area where we thought that we'd found the slump, and we interpreted that as the fact that the seabed had moved. There was a lot of fluid coming out, and these things, it was just like buying your bijou residence in London. So this was a great place for them. And just a video here. You can see on the top right, we're at 1,647 meters, and this is an octopus down there. And he's having quite a lazy time because his lunch has been delivered to him by the slump failure. And you can see all these mussels around here. And again, all this sort of evidence we used to determine that the seabed here hadn't moved recently. Here we are, these are these modiolis, and they're something like maybe about 5-6 centimeters. And I dived on this, and that was one of the most exciting experiences of my life. And not only did we carry out the mapping, but previous to Papua New Guinea, we couldn't really model tsunamis from submarine landslides. Earthquakes are very simple because you have an instantaneous input of energy into the water column. And so you get a step which is formed instantaneously, and the tsunami just travels outwards. The problems with submarine landslides is they travel much slower. So my colleagues had to develop the mathematics to actually input that energy into the water column, and there's been quite a lot of discussion about how we actually do that. And so not only did we identify the actual seabed failure, but we also modelled it, and you can see on the left-hand side there's the big yellow dot just above amphitheatre is the source, and you can see down the bottom left there, that's a Susana lagoon, and you can see that from the right-hand scale that the tsunami there was modelled to something like about 14 metres, and we knew from measurements on shore that the actual highest height was something like up to 15. And below that colour figure there, you can see the model from the line and the dots, which are from the measurements. And there was quite a good correlation there. And PNG was seminal. It was one of the most important recent events because it's the first time, really, that we have properly identified seabed sediment failure as a tsunami source. And it was using the new technology that was available to us. And at the time, a lot of my fellow scientists wouldn't believe it. So, following on. The Indian Ocean. I've already mentioned that, and this is one of the most destructive tsunami we know. I've already mentioned Banda Aceh, and this is an image looking from the town seawards, and all that destruction is from the tsunami. It's not from the earthquake. It's all from the tsunami. And the tsunami heights here were massive, 15 to 20 meters. And there you can see, as a colleague of mine, Jose Barrero, you can see in that figure there that the tree line and the bare rock below it, that's where the tsunami reached, and it was stripped. And Jose, and you can see him on the right-hand side, he's 2 meters tall. When we get this stripping of the trees, that gives us the information about how the actual tsunami was. And you can see here it's about something like 2, 4, 6, 10, 15 meters high. And here in the Indian Ocean, it was a massive seabed rupture, and it was about 1,300 kilometers. And if you want an idea of the scale, that's what it's like. So you were living in the Isle of Wight, and the rupture started there. 4 or 5 minutes later, it propagated out northwards of the Shetland Islands. This was a huge rupture, and the earthquake, as I've said, was a magnitude 9.2. I've already shown you this slide, but it reinforces it. Those people in India, Sri Lanka, and Thailand should not have died. There should have been a warning system, and actually Indian Ocean had argued over it for about 3 years previous to the 2004 event. And again, comes back to this figure here, Indian Ocean, magnitude 9. And it was a benchmark because we realized that we weren't as smart as we think we were, because it wasn't predicted that this magnitude earthquake would actually take place at this location. As I say, it's 1,300 kilometers, but on the bottom right little figure there, and you'll notice there are 3 little rectangles there. And what happened is the tsunami started on the bottom one, and it moved through the first rectangle, which is what we call a plate segment. Convergent margin areas are segmented by transverse orthogonal faults. And then it jumped to the next segment, and then it jumped to the next segment. And we didn't realize that this could happen. And so we had this massive earthquake, which was again beyond our understanding. And this figure here was 1980, and certainly in 2004, indicates what we thought about earthquakes. And the horizontal scale is the age of the Earth's crust and ocean crust. And on the bottom, it's young, and on the right, it's young, and on the left, it's old. And again, on the vertical scale is the rate of plate convergence, and that is how these 2 big crustal segments come together. And our understanding was that large earthquakes only occur on the top right. And there you can see it's rapidly moving crust, and it's young. And you can see that the figure on the extreme top right is a 9.5 magnitude, 1960 earthquake. And small earthquakes occurred on the left-hand side along, for example, the Western Pacific. And the Indian Ocean earthquake happened there. And everyone said, why? And it's to do with the age of the Earth's crust. I'm not going to go into too much detail, but you can see along these mid-ocean ridges where crust is formed, and it's red, it's young. And as you move outwards, for example, in the Western Atlantic and also in the Western Pacific, it's old. And if you look down, I'm not sure it's very glorious. And you can see if you look at Sumatra, then the crust is actually quite old, and I think it's something like about 40 million years, something like that. And the Indian Ocean event led to a major revision of our understanding of where these great earthquakes occur. I'm not going to go into too much detail, but it disproved the model that I showed you, the Ruffin-Kanamoy model, that young crust traveling quickly is the only location where you find these great earthquakes. And there are lots of controls on it. One of them is that we have historical records of earthquakes and tsunamis, but these events take place over geological timescales of thousands, if not tens of thousands of years, and this record is too short. And what we need, or what we don't want, is new events which will make us wiser. And this is another figure here. It was carried out by a colleague of mine who looked actually at the information that we had. And on the basis of this, and the dots are obviously earthquakes, and the larger the dot and the redder, the greater magnitude. And he said, basically, we really can't base our understanding on historical timescales. The end result of the Indian Ocean was now a warning system there, and it's operating, and obviously people travelling there, both local people and obviously people who are visiting, have a warning. And this is something I used to show, and this is the ultimate must-have. You have your mobile phone or your iPhone now, this is out of date now, and which can actually give you a warning. Here we are, region Indian Ocean, magnitude 7.1, areas affected. And now there is certainly websites now where you can, where we are informed. And we develop new models of tsunami, how they are generated and how they travel across the ocean. The Indian Ocean event led to a major reappraisal, and not just in the Indian Ocean, but also other areas. On what you can see here on the top left is the Indian Ocean, and the comparison was made with the northeastern Pacific, Cascadia, which is an area where we know there is a major tsunami hazard. And I've mentioned timescales, and one of the other aspects that came to the fore is that we have these historical records, historical timescales, but when the tsunamis travel in over land, they lay down sediment. And here's a tsunami sediment off of Cascadia up in the northeast area. And what we can do now, if we can date these and we can identify them, we can extend our understanding back over tens of thousands of years. And on the left-hand side here, what we've got is it's like a section, and we've identified, or my colleagues have identified, a whole number of those tsunami sands, and the oldest date is 7,770, and we work out the averages. And these are 13 of these major events, the average of 500 to 600 years, but some as close as 200 years. And the problem here is the last major event was 1700, so we're something like about 400 years away from a major tsunami, and they're very concerned there that we're going to have another large event. And again, with the new modelling, they have developed improved mitigation strategies of warning people. And previous to the Indian Ocean, the safe height people were advised to go to were 10 metres, and you can see from the figure on the right there that now you're certainly up to 20 or 30 metres. So previous to the Indian Ocean, people at 10 metres, if there had been an evacuation or warming, would have died. So this is another figure here which exemplifies that. Post-Indian Ocean, again, major review globally. Great earthquakes might occur anyway. There are new models. And a good colleague of mine, American, who told me that he treats me like a little boy. You know, he's only about a few years older than me. And he said to me in Japan a few years ago, David, you've been very fortunate. For the first 30 years of my career, I tried to persuade people that tsunami was a major hazard. Now, over the past 10 years, we've seen that they really are. So again, we are benefiting from these dramatic events. And this is a model now. What happens is that the red lines are these subduction zones, convergent margins, where we expect to have large earthquakes. And based on there we go. These are the major plate boundaries. And based on our understanding of historical records, there have been modelled tsunamis along potential ruptures where the earthquakes might take place. And so they've looked at the tsunami record. And then what they've done, my colleagues, if they have, there we are, there's also now more buoys in the ocean which can measure the tsunamis, and there are also tide gauges. And we have this pre-computed database. And what happened, there's a lot of money spent on looking possible large earthquakes and where they will occur, and then modelling the actual tsunami. And so what happens now on the bottom left there is one of these buoys which floats on the ocean and is there to actually record any unusual perturbation of the sea surface, which might be due to a tsunami. And if there is a major earthquake, what happens is that they immediately look at this pre-computed database to see if there's any danger. They look at the actual model of the tsunami, where it will travel to, where it will strike, and obviously they can give out a warning. And here's a real-time event. I think it's 1980, and what you can see here is there's been an earthquake somewhere. And there are the buoys, which are the yellow triangles, and you can see that the observed is blue and the model is red, and we get an immediate comparison. And from the comparison of that, as a tsunami travels outwards, and it's a starburst effect that you can see, we can track the tsunami. And as I've said, over hours and hours and hours, within this timescale, we can actually give adequate warning. And here's the earthquake here. It's off of Kamchatka. And again, there's more information which is being recorded and computed. And today, in the best circumstances, if there's a very large earthquake, then they can give a warning certainly within 3 minutes. And the warning system basically works on one center, and this is in Honolulu, giving out a warning. There is a dangerous tsunami to centers, local centers around the Pacific, and it's up to the local authorities to decide what they can do. But if you get a warning within 5-10 minutes and you know the tsunami is going to strike in 15 hours, then you can track it, and then you can make some decision about whether you start moving people away from the actual coastlines. This just follows that. And again, you can see here that a very large tsunami, my arrows have moved a little bit, but okay, it's 15 hours warning from Chile to Hawaii, and again from the North Pacific, it's about 4.5 hours. So there is time to actually warn. What you have here are the black dots. The blue dots are the seismographs, which are recording the earthquakes, and the actual blue dots are the tide gauges, which are measuring or looking for unusual perturbations, which might indicate that there is a tsunami. But one of the drawbacks is it's still distantly sourced tsunamis. If you have a local earthquake, then maybe it strikes in 20 or 40 minutes. We still have problems there. So since the Indian Ocean, there have been a lot of advances. In the picture here shows where the actual earthquakes occur and where there has been tsunamis generated. So now in all the major oceans, the Pacific, the Mediterranean, and the Atlantic and the Caribbean, they all have warning systems. But the problem is it's still based on earthquakes. I've already shown you that we know that submarine landslides are very dangerous, and we still have problems there because the tsunamis generated will strike very rapidly local coastlines, and it's very difficult to actually warn against these. And one of the other problems is these major events over longer time scales, they are low frequency, but they have high impact. And whereas with storms, we can track weather systems, we can give warnings, and we can model them fairly accurately. These may be high impact but high frequency. We still have problems in dealing with these low frequency, high impact events, still problems with near field warning. And one of our major questions is, where will the next large event strike? Well, after the Indian Ocean, we're all pretty amazed when the next major event struck Japan. And there's a figure here showing us the Sendai Plain, where I've been working. I've been out there 4 times. Struck with devastating impact. This is Uriagi and on the Sendai Plain here before, and you can see afterwards. And you can see that most of the buildings are destroyed, and the white buildings, the long ones, are the concrete ones. A lot of these buildings were wooden. And again, a modelling of this, we've been working here. I've just shown you the location. The tsunami came in at the coastline. It was 11 metres high. And as it flooded inland, it inundated this area, and it was for 5 kilometres. So it was absolutely devastating. And immediately there was the response, and the figure here shows the actual tsunami heights at the coast. It's what we call the actual run-up. And you can see on the bottom left there, which is where I was showing you the figure, the tsunami heights, the actual bars there are quite low, and they're something like about 10 or 12 metres. But further to the right, you can see on the Sanriku coastline there, the tsunami was up to 40 metres high when it penetrated inland. And this is a figure here, Minami Sanriku, which I visited a number of times, and you can see the devastating effect. What we saw here, there was a funneling because it's a bit like Cornwall. And when the tsunami came in, it was focused up one of the rear coastlines. But all this devastation here was actually caused by the tsunami. And I think something like about 1,500 people died. And the tsunami at the coast was maybe 10, 15 metres, but as it travelled inland and it was focused, the wave built up. and in the end it was 40 meters high. And of course the impact in Japan, on the right you see one of the tsunami walls, the defensive embankment which was built to defend, being overtopped, and the bottom right is again the Sendai plain. I've shown you figures, but 16,000 dead, 3,000 missing, and of course the destruction and how much it will cost actually to repair. And of course one of the major aspects is the Fukushima nuclear power station, which was devastated because the backup generators were flooded by the tsunami wave, because they felt that the location the generators were placed in was safe from inundation. The Japan tsunami was only devastating close to source. There's a figure here, and in the middle you can see the black little dots sort of just to the right is Hawaii, and if the actual rupture had been a different orientation, then it could have struck Hawaii with devastating consequences. But fortunately the wave travelled southeastwards, okay. And the perspectives with Japan was the Indian Ocean was certainly a major surprise, but Japan was too, because it comes back to one of my comments. This doesn't happen to first world countries, particularly those which are really very, very well prepared. But obviously here that the earthquake magnitude was underestimated. They thought that the highest magnitude would be a magnitude 8, magnitude 9, and that's not an arithmetic scale, it's a logarithmic scale, so the 9 was 30 times, the earthquake was 30 times larger than the magnitude 8, and again we were surprised, and that went for Papua New Guinea, and it went for the Indian Ocean, and it came back to haunt us with Japan. And again, coming back to this figure, where we find these largest earthquakes, and that's what the one I showed you last time, and again Japan was there. So it certainly confirmed our understandings that we had developed from the Indian Ocean event. But with Japan, and my theme of my talk is learning from recent events, is do we fully understand now? It's probably the most comprehensively geophysically recorded. I think they have something like 2,000 seismographic stations. They have geodetic recording systems, so global and local seismic networks. They have onshore tide gauges, and they have these offshore pressure gauges. So they're off the coastline, and when a wave passes over, it measures them, and obviously when the tsunami went by, that's been recorded. And also these dart buoys, which I've shown you, were also offshore. And so far, there's been 150 science papers published. And what I'm going to tell you now is all new research, which I've been involved in. I've been working onshore, but so there's still uncertainty in the earthquake generating mechanism. And what I'll show you here is the figure on the left you've seen, which shows the run-ups. But one of the major problems is the relationship between the earthquake rupture and the highest run-ups. And the highest run-ups are here, but if you notice the earthquake rupture here. And modelling indicates certainly that the earthquake might not be able to generate those very, very high run-ups in the northern part of Honshu Island. And this is a figure, colleague of mine, Loveholt. And what he's tried to do here is he has modelled the tsunami from the earthquake rupture, but he can't do it. So what he's done is he's changed the earthquake rupture. It's what we call fixing in science. And for most esoteric science, it's okay, but when you're dealing with human lives, it's really not. And so a lot of the models, which are based on adjusted earthquake sources. Okay, I won't go into too many details. And one of the other measurements is, rather than modeling the tsunami on the earthquake, they look at this wave data from the GPS buoys or the tide gauges. They invert these, and then they try and get the actual rupture from these. And this doesn't work either. So colleagues of mine have suggested that there might be another generating mechanism, and I've just told you about Papua New Guinea. And one of the obvious potential alternate or additional mechanisms, the tsunami can be generated by most of the earthquake, might be a submarine landslide. So we've gone offshore, and you can see the maximum run up there. The star is the earthquake epicenter. And is there a what we call a submarine mass failure or a submarine landslide? And we've looked for it. And I showed you the bathymetry that we had from Papua New Guinea. Of course, with Japan, there's a huge amount of offshore bathymetric data, which I can show in this figure. And it's obvious that what we've tried to do is is there a major submarine failure where the ellipse is, which maybe relates to the arrow, which shows you where the maximum run-ups are. And what we've done here, looking at this, we've actually found that there are a number of these submarine mass failures. But the most important one is here, and it fits in where we have the highest run-ups. I'm not going to go in again in too much detail. We've done a huge amount of modelling, and is this going to work? Okay. So what we've done here is what you see is a model of the earthquake, which is tsunami, which is linear, and we've also superimposed that a model of a submarine landslide, which fails 300 seconds, about 5 minutes afterwards. And modelling this actually provides the actual run-ups that we've actually observed and measured off of the northern coast of Honshu Island. And here's a figure here which shows on the right-hand side the actual tsunami heights, and the black dots are those measured, and the red dots are those which is the tsunami heights calculated by using just the earthquake. And you can see that certainly on the right-hand side, between 39 and 40 degrees north, you can see they don't fit. But if we superimpose upon that a submarine landslide, we get some better approximation. And I showed you this video earlier. Look quickly, you'll see the tsunami waves come in, the land is already inundated. And this indicates that actually that there was that supports our thesis that there is two tsunami mechanisms. The inundation, which you saw briefly, was from the earthquake, and maybe these waves are coming in from the actual submarine landslide. Our object of research is to determine the hazard, and it's very exciting and very interesting. There's no doubt about that. But really what we scientists like to do is try and use it for hazard mitigation. What has this got to do with it? Well, I regard Legoland as a reflection of our culture. And whereas we have pirate Legolands and Star Wars Legolands, I know that tsunamis have struck home with a younger generation when we have Legolands which are used in modelling or demonstrating tsunamis. It's all right. No one was damaged. Okay. It's humorous, but it's quite good because children are, we show that we actually use this in some of our demonstrations when we have open days. So lessons learned, okay. Number of devastating events. Do we live in the age of tsunamis? Perhaps. They're well studied, and there's no doubt that we're improving our understanding. Still the main cause are earthquakes, but recognise new mechanisms. I haven't mentioned volcanoes because, I study those because we had only small tsunamis, Stromboli in 2002 from earthquake collapse. But certainly seabed slumps or seabed sediment failures are certainly a major hazard. The importance of the new events is that this guides us, this improves our understanding. But it's not only that, it's a technology. And one of the most, I think it was Ernest Rutherford who said that science is physics and everything else is stamp collecting. Well, we certainly need stamp collecting if I better understand tsunamis, but also new technology. And again, these are leading to better mitigation strategies. But even in the best prepared countries, these events can be major hazards and, of course, disastrous. And it's also the societal impact which is on countries like ourselves. There is some danger, but minimum danger from tsunamis, but we're certainly aware of them, and it's now us as well as them. And part of this, of course, is instantaneous media access. I often get phone calls at 10 o'clock at night saying, has there been an earthquake in the Pacific Ocean? Is there a tsunami? And I just say, I don't know. I go on the internet and look at it, and then they have some sort of interview. And also there's a fascination with these cataclysmic events, which I guess is why a lot of you are here. And also more videos. It's not just a recording by by seismographs or geodetically, but also we've had photographs, videos, Indian Ocean and also Japan, and we have them instantaneously. And I guess as tsunami scientists and scientists generally, we have to accept some sort of hubris because we are not as smart as we really think we are. And there's still a lot that we have to learn. And the future, there's still lots to learn. And what about the future? Submarine landslides, not all of our ocean margins are mapped in detail, 20 or 30%, and we still don't really fully understand how hazardous these are. Is there going to be another major submarine landslide? We've had one off of Newfoundland, we've had one off of in Papua New Guinea, and there are other events which we think might be. There's one in Java, there's one off America, and colleagues of mine were talking today that there may be a submarine landslide tsunami in the 16th century near Lisbon. And one of the major problems is they're really dangerous because they can occur anywhere. We really don't understand them. They can have very large volumes. One of the largest tsunamis to strike Britain was 8,200 years ago. The waves were something like 20 or 30 metres off of the coast of Scotland, very close to where we are living, and the volume of this landslide was on like 2,500 cubic kilometres. It's large, the area of Scotland. They're unpredictable, and it's very difficult to actually prepare for them. Some of you will have seen the programme on the Convergence volcano, and there have been a lot of arguments between scientists about whether the collapse of volcanoes can create very large tsunamis. We know, and this is the Canary Islands, and we know that they can locally. If you get a major collapse on one of the Canary Islands, I've been studying Gran Canaria, and there we have tsunami sediments 180 metres above sea level. But the major problem is what happens when the tsunami travels farther afield, and this is just a bit of a review of papers published since 2001 where the scientists have said yes or no, yes or no, yes or no, and we still really need to work here. And one of the major aspects we have to consider is global warming and the impact on seabed slope stabilities. And on the left-hand side there's a figure of where we know submarine landslides are off the coast of northwest Europe. And on the right, it's predicted temperature change by the 2090s. This is a little bit out of date. This was a figure about 5 years old. But you can see that the largest warming is going to take place in the high latitudes, and that's where we know there are large sediment volumes. And is the global warming, going to impact upon ocean temperatures, and will the ocean temperatures impact the seabed? And will the warming destabilize the sediment, and we would be more prone to submarine landslides? I started out with tsunamis. What are they? You all will have some idea or improved understanding after this talk, so most of you know, and I'll finish there. Thank you.
Well, thank you, David, for a tour de force. Covering the wide range of subject matter that constituted by tsunamis. Before we take questions, I think we can, Una, invite people from the overflow room if they want to come in, please.
If they have a question.
Yeah, if they have a question, right. So the way we'll do it, we have a couple of people there and Una with microphones. So that if you have a question, please keep it short and speak clearly and hold the microphone close so that we can all hear the question, please. And just wait till we get the microphone. So Una, please here.
Thank you very much for a very exciting presentation. I'm a Consul General of most tsunami-prone country. And my question is, I understand now early warning system started working. And is there any specific example where, because of this early warning system, actually many lives were saved? Thank you very much.
Yes, it's a good question, and the best example is Japan, 2011. And the warning was given, and the way I look at Japan is that 20,000 people died, well, 19,000 people. And although there were misunderstandings about the source and a lot of people died, I sort of look at it in the fact that rather than 220,000 people, 20,000 people dying, maybe 200,000 people were saved. So, and it's what I said, is our understanding improves with each event. The warning systems are the best that we have, and certainly again after the Indian Ocean and again after Japan, we're working on improving them. And so yes, there are examples. One of the major problems with warning systems is he's evacuating people, and there's no tsunami, and that's still a real problem because people then lose confidence. And still, one of the major problems is in the near field, in where you have the earthquake or the submarine landslide source. And generally speaking, there are these highly sophisticated warning systems with all the seismographs, tide gauges. But if you're ever in an area where you know there's likely to be a tsunami and you feel an earthquake, then I'm not going to use the term I usually use, but you can move quickly and get away from the coast. And I think that's the best advice. The problem is there are some very dangerous earthquakes which you cannot feel. But if you're in an earthquake area and you feel the shaking and you're on the coast, then just walk or get to a high land, get somewhere of improved safety. Thank you.
Any more questions? Right, just here at the right, thank you.
It's based around the same question about mitigation. You've only highlighted alarms. Is that because you think that other sorts of defences that Japan were trying aren't possible to put into other countries? Or modelling must allow you to see the effect of a tsunami on the land and therefore maybe mitigate against it that way. Is that not a possibility?
Yeah, sure. And again, yeah, okay. Japan is tsunami prone, it's what I've said. And Japan has taken a technological approach, and they built the tsunami walls, and the tsunami walls were overtopped, and that is one way of doing it. And certainly Japan over the past, since 2011, has rebuilt a lot of the tsunami walls, and that is one way to mitigate against that. But whether any other country would be prepared to do that, I don't know. But there are, yes, you can build hard engineering structures. One of the problems my research identified is that if you have an embankment and you have a wave which overtops it, then what happens is that the back of the embankment is undermined and it collapses. And so what happens, it's really not that much protection. So the embankment has to be higher than the actual tsunami wave. So yeah, you can use hard engineering. That's an alternative. I think, was that your question? Yeah.
There was a question here, yeah?
With the Boxing Day 2004 event in the Indian Ocean, it was interesting that Nature, the weekly magazine, ran a story, I think early January 2005, about a chap who was a seismologist sitting eating breakfast in a hotel on the east coast of Sri Lanka. And he felt a tremor and said to his wife, "I think there must have been an earthquake somewhere." He was on holiday. She, not him, but she, his wife, went to the hotel management and said, "My husband thinks there's been an earthquake, you better get everybody off the coast." And that hotel did, and they didn't lose anybody. So Nature picked that up and ran it as quite a story. I don't know if you remember that, Dave, but it was quite a story, and maybe there's a lesson there for us all.
Yeah, sure. Undoubtedly, he felt the earthquake, and actually, the Indian Ocean earthquake was felt as far away as I think as Africa. So, yeah, sure, he felt the earthquake. Again, it's what I said. If you feel an earthquake, and if he had geological knowledge, then he would know that along the east coast of Sri Lanka, it was unlikely, unless it was a submarine landslide, of course, that there would be an earthquake-generated tsunami. So, yeah, it's a case in point, and it's a positive case, certainly.
Right. If I understand correctly from your map with the submarine landslides, there seemed to be a significant risk along the coast of Norway. Is that the case? And if so, what would happen if one of them happened? Yeah,
there is a significant risk, and I mentioned the landslide of 8,200 years ago, the Storegga landslide. That was huge, and when it failed, it created a tsunami, which certainly along the northeast coast of Scotland, the Faroes, and the Shetland Islands was tens of meters high. There are a number of landslides there, and as I showed you on the map, all the way down the northwest European margin, there are landslides. We have a good understanding of why they're there, and they're to do their climate, to a large extent, climate generated. And I mentioned showed in my final slide the effects of global warming and what that might have on ocean temperatures, sea bottom temperatures, and therefore slope stabilities. And actually, there's a major UK-funded program which is entitled "The Effects of Global Warming on Seabed Stability in the North Atlantic." So yes, we are very concerned about it. I mentioned there are a number of landslides. The most recent one is only 2,600 years ago. And so, which in geological timescale is like yesterday. So yes, there is a hazard. We think it's small, but what I always tell people is that we've had 4 or 5 major events over the past 10 or 15 years, and we haven't predicted any of them. So I'm always very cautious.
Okay, one question up the back there, please.
Do you think your Age of Tsunamis is a matter of perception and better scientific recording, or do you think that some of them are due to submarine landslides, as you say, perhaps linked to climate warming? But given that I suppose most of them are due to earthquakes, I don't imagine anyone's yet linked plate tectonics to global warming.
No. I'd say with earthquake-generated tsunamis are tectonically induced and to do with inner plate mechanics, sure. Submarine landslides, they're usually triggered by earthquakes, but it's the global warming which could have some impact on the condition of the sediments which are likely to fail. And as I've said, we still don't fully understand these. We know that the sediment is laid down. And then over periods of time, tens of hundreds of years, thousands of years, then the actual sediment properties change. We know over the 100,000-year time scales, we have the interglacial, glacial cycles where sea level changes up to 120 meters. And obviously this is a control by climate. But no, earthquakes as far, I don't know. Sea level change can affect the loading of the oceanic crust, and there's indications that this certainly can perhaps contribute to creating an earthquake, and there's a lot of discussion about this. But as far as submarine landslides are concerned, there's a lot of climate control, controlling sedimentation over tens of thousands, maybe hundreds of thousands of years. But as far as we're aware, you still need something to kick it off. And the most likely cause is an earthquake. But I showed you Cyclone Camille, 1969, where that was caused by a low-pressure system. And what happens there is if you have low-pressure systems moving over the ocean, then the loading, you get increase in sea level as it rises up, which means you get a decrease in you get a decrease in sea level, and you get a decrease in the loading, and then what you can have is that, as we know, can actually generate a submarine landslide. So there is that control. There's also tidal changes if you have particularly unstable sediments. But earthquakes generally inner Earth processes, although there's a lot of research now which indicates that they might be related to climate change. But submarine landslides generally are still sedimentation controlled by climate over latitudinal changes, but also temporal changes.
I think we'll leave this on that quite contentious point, a neat question in relationships between climate change and plate tectonics. Nice point. I'd like now to call on Robert Gapliff from the British Geological Survey and to ask Bob to pass a vote of thanks.
Dave, that was fantastic. I've got I've given 10 minutes on the slot, so I thought I'd have to come up with a story, just a little one. In 1988, I went out to start a job in Tonga, and the person who'd had that job for the 4 years before me was Dave, and he met me at the airport, and he took me to the house where I was going to live, where he'd lived. And right in front of the house is a reef flat, and then the Pacific going for ages. And you may have noticed that Tonga was on lots of his diagrams as one of the places that might have it. And I think Dave lived there for 4.5 years, looking out, waiting for a tsunami. And I don't think you had one, did you? No. And I didn't have one either, thank goodness. But I think waiting for a tsunami for 4 years probably got him on on the road to doing that research. And he's too modest to say that he's still going, but he is one of the proponents of the research that's coming up, looking at the North Atlantic, and there are a couple more of you in the audience who are going to work on that one. And I think that research will be really useful in the next few years at assessing the risk, certainly for Norway and maybe for those of us that live in Portobello as well. But Dave, magnificent, thank you very much, and thank you for coming up, and we're looking forward to some more publications on tsunamis in the near future. Thank you. Thank you very much.
Thank you, Bob. With that, we'll call an end to this part of the proceedings. You are now all invited upstairs for some refreshments. We'll be heading upstairs to the welcome rooms. Thanks again.